Okay, Algebra 2 students, today we are looking at Unit 3, a Unit 3 review, and this in large part, the entire unit was review of Algebra 1 topics. So if you had taken care of business in Algebra 1, then this unit was a piece of cake. Unfortunately, some of you kind of blew off your Algebra 1 or assumed the day you walked out of Algebra 1 you no longer needed it and just did a complete brain dump of it. Okay, but it was all about the properties of lines and graphing lines, and so none of this was really a new concept. So we started off with a basic discussion about slope. And of course, you got your slope-intercept form. Some of you are still a little confused of what's the difference between slope and slope-intercept form. Well, slope is part of the slope-intercept form. Of course, slope-intercept form is y equals mx plus b. And the basics of a line is it needs two things to do what it does. It needs somewhere to begin, and it needs somewhere to go. Now, somewhere to begin or somewhere to start, that is your y-intercept. Your y-intercept is what anchors your line to the graph in the graph. Somewhere to go is, as it leaves the y-intercept, our slope tells it which direction to go and how fast to go there. So we started off with a discussion on slope. Okay, and one of the first things we did is we looked at the several synonyms that exist for slope. Okay, now some old junior high ways of doing things. Of course, a problem could actually ask you for slope by using the word slope, but that's probably a little bit unrealistic. They could also use the algebraic variable m from slope-intercept form, y equals m x plus b. Okay, but again, pretty unrealistic because slope-intercept form exists on most formula charts, so they're probably not going to hand it to you and then ask you about it. Okay, the old way that you learned it in junior high, rise over run. But again, probably a little unrealistic to hope for them to ask for rise over run because they know that that's how everybody learned it. Now, they could actually use the formula like you see there on number 4. Okay, if you know 2 points that are on a line, of course, point 1 lives at x1, y1, and point 2 lives at x2, y2. And if you take those coordinates and plug them into the formula shown there on number 4, y2 minus y1 over x2 minus x1, that is actually how slope is calculated based upon 2 points on the line. So I have seen a few questions actually bust out the slope formula asking you about the slope. Okay, in written form, slope would be stated change in y over change in x. Now, if you look back at the formula on number 4, that's exactly what number 4 shows, y2 minus y1 in the numerator. That is, as you go from one point to another, how much does the y value change? And then in the denominator, x2 minus x1, as you move from one point to another, how much does the x value change? So that is the change in the y values over the change in the x values, exactly like it says in number 5, change in y over change in x. Okay, a little bit more scientific notation on number 6. They've brought the Greek letter delta into the equation here, and delta represents change. So in symbolic notation, number 6 says change in y over change in x, which is exactly what number 5 says, which is exactly what number 4 says. Okay, the kind of flavor of the month term that they have been using for the last couple of years or so is when they refer to slope, especially in a word problem, their tendency has been to call it rate of change. Okay, these are all synonyms for slope. They are just as likely to ask any of them as any others. Okay, but do expect that if they try to ask you about slope in a problem, it's probably going to be one of the last 4 examples here as opposed to one of the first 3. Okay, now slope is a fraction whether it's written as 1 or not, as is indicated by the formula, change in y over change in x. Okay, so we should expect it to be a ratio, even if it's not written as 1. Of course, remember, anything that does not automatically or does not expressly have a denominator automatically has a 1 in the denominator. And you can tell a lot just by looking at the slope value in an equation. If your slope value, and of course when you're in slope-intercept form, slope is the coefficient in front of x. If you have a positive coefficient, that means your graph is rising as you read the graph from left to right. That's how we read our graphs, always from left to right. Okay, if it's positive, your graph is rising from left to right, and if it is negative, your graph is falling as you read from left to right. And that's the difference between a positive numerator or a negative numerator, so a positive rise or a negative rise. Okay, if your value itself, okay, 1 is the parent function value for slope. Okay, so as we adjust from one direction or the other, our graph is going to change. If you're looking at a value that is larger than 1, what that means is your rise is moving faster than your run. Your numerator is bigger than your denominator. That's going to cause the graph to go to infinity or negative infinity faster than it should have. So we're going to be looking at a steeper line. If your value, your slope value, gets smaller than 1, that means your run is larger than your rise. So your denominator is bigger than your numerator. And that's going to cause the graph to become more horizontal. And as a result, it is not going up or down to infinity as fast as it should be. Okay, a couple of exceptions to the slope rule, or not exceptions, but special cases. Okay, if your rise tries to zero out, in other words, the graph will not move upwards or downwards, we of course end up with a horizontal line. And the official term for a horizontal line as far as slope is concerned is zero slope. And that makes sense because your slope fraction has a 0 in the numerator, and any fraction that has a 0 for a numerator, it has no value. So we simply say that fraction is worth 0. Okay, those of you that may have learned an older term where y'all called that graph a horizontal line no slope, you need to remove no slope from your vocabulary. That has been deemed to be an incorrect description of a horizontal line. Vertical line, we have the opposite situation. The graph is definitely rising, but it refuses to run. And that means our denominator is equal to 0. And as we've already seen through our discussions of asymptotes, we do not allow denominators to equal 0. Okay, so we say that our slope in that case is undefined, which basically means uncountable. Okay, and that means it's not going to plug into our equation the way we would like it to. Okay, so we looked at several examples about how to calculate slope, and you can look back at those examples, review that video on slope if you need to. Okay, continuing on the next time with equations of lines. Okay, so we are now looking at a couple of special cases of the equations themselves. We talked about what happens with the slope of horizontal and vertical lines, so let's see what happens with their equations now. Now we said a horizontal line is going to have a slope value of 0 because it refuses to rise. It is running, so there is a denominator, but there is no numerator because it will not rise. That causes the slope fraction to be a 0. Well, remember, slope is just the coefficient in front of x. So if your slope is 0, that means you have 0 x's in the problem, so they will not even show up. So you'll end up with an equation that says something like y equals -4. Okay, and an even easier way to think about a horizontal line is that it only makes contact with one axis. That axis is the y-axis, so its equation is going to say y equals, and then the number that it equals will be wherever it crosses the y-axis at. In this case, y equals -4. Okay, same thing with the vertical line, although you cannot actually use the slope-intercept form for a vertical line, and that is because our slope value is undefined. You cannot plug an undefined value into an equation without wrecking the equation. Okay, but once again, think about it like this. The vertical line only crosses one axis. That would be the x-axis. So our equation will be x equals, and then wherever the line crosses the x-axis. In the bottom case, that would be a 3. X equals 3. Okay, now it's very easy to plug into the equation, okay, if you know your slope value and if you know your y-intercept value. The real challenge is what happens when you do not know your slope or your y-intercept. Well, we already know how to find the slope. Very easy. We just plug into the y2 minus y1 over x2 minus x1 equation. But what do you do if your y-intercept is unknown as well? And the answer is really a very simple one, like you're seeing at the bottom of the screen there. Any point that you know for a fact exists on a graph of any kind, then you can take the ordered pair for that coordinate and you can plug in to the equation that the coordinate is on. Okay, so that means if you know that you have an x comma y that exists on a line like we're looking at here, then you can take that coordinate and you can plug the x value in for x and plug the y value in for y and solve the equation from there. So like you're seeing there, we selected one of the points, plugged in for the x and the y value, and that gave you an equation that now only has one variable in it, and that one variable would be your y-intercept. If you go through your 5 steps and solve your equation for your y-intercept, you will then have your b value. You already knew m, you now know b. You can plug into y equals mx plus b, slope-intercept form, and you have your equation. If you have any trouble with this, which I know some people still do, you probably need to rework some problems, possibly watch the video for equations of lines and get that problem ironed out. Okay, now a little bit of extra information on slopes. Okay, you may not have known this one from back in Algebra 1, or you might have, just depends on your Algebra 1 teacher, but it's a fairly simple concept, just a couple of facts we need to know. The behavior of lines in a graph is controlled by the slope value. We've already said slope tells us whether a line rises or falls as it moves from left to right. It tells us how much it rises or falls as it moves from left to right. So if you have two lines running around in a graph together, then their behaviors in respect to each other are going to be dictated by their slope values. So if two lines wanted to be parallel in a graph, meaning of course that they're going to be in that graph and they are never going to intersect each other, that means they are behaving exactly the same way. They must be rising and running at exactly the same speed. So in order to be parallel, two lines are going to have the same slope values. In order to intersect, all they're going to have is different slopes. But if they want to intersect and form a right angle, be perpendicular to each other, then they're going to have to intersect in a specific way. And the only way to get that to happen is if the slope values are negative reciprocals of each other. Meaning, if you take one of the slope values and ask yourself, if I changed the sign and turned the fraction upside down, would that give me the slope from the other line? If it does, then you have two lines that are perpendicular. If it does not, then you have two lines that are not perpendicular. Okay, so the rest of this was just looking at those rules in action. Slopes must be the same to be parallel. They must be negative reciprocals of each other in order to be perpendicular. Okay, we actually spent several days in there working on equations of graphs. We had some activities out in the hall and up on the back wall and stuff like that. And then that brought us into word problems. Okay, graphing lines and equations of lines is one of word problems' favorite places to live at. Okay, so a lot of times when we are asked to write an equation from a word problem, chances are we are graphing a linear equation. So we are going to have to build slope-intercept form from a word problem. So I offered you a basic strategy, and this was completely up to you if you wanted to use my strategy or not. If you have a strategy that has worked well for you in the past, you certainly do not have to use mine, but if you don't have one, please consider using this one. And the strategy was really very simple. Okay, first off, I do not not want you to try to tackle anything the first time you give the problem a reading. Do not think about any math. Do not think about anything other than simply reading the words. Comprehend the English language of the problem. Okay, so we are simply reading the words our first time through. If we run into something we do not understand, try to break it down. See if you know the prefix of the word or the root of the word, and see if you can't assemble a meaning, especially if you believe it is something that is critical to understanding the problem. Second time through, you're going to go back and now we're going to actually read the problem itself, meaning our brain is going to try to organize some of the math, identify a few of the things that we think are going to be important, stuff like that. Okay, and possibly during that pass or maybe even a third time through the problem, now identify the relevant information. Okay, highlight or circle values that you believe are going to be critical to the solving of the problem or the assembling of the equation, stuff like that. Step 4 would be to interpret the information that you identified. Okay, the value that you identified, do you believe that will be the movement of the graph? Is that slope? Or do you believe you've identified a fixed point in space, maybe the y-intercept, stuff like that, and then relate the information, which means how will this information interact with each other in an equation? Okay, so as you go through, and definitely before you work any problems or write any equations, you ought to be identifying fixed locations and movement the graph is going to experience. And those are, of course, M and B, your slope and your y-intercept. Okay, so we worked through several problems a step at a time, and you may want to go back and view that video if you're still struggling with this. Okay, but you're going to see on every one of the problems that we worked, read the words, read the problem, identify relevant information, interpret the information, relate the information, and are there any fixed locations in the graph? Is there any movement in the graph? And every single word problem, okay, you saw the exact same 5 steps and the exact same 2 questions to address, okay, before the problem came to an end. Anyway, as I said at the beginning, this was largely review. Linear equations are nothing new. You've been doing them since pre-algebra and algebra 1, and most assuredly again in algebra 2. So not a lot of new information except for the possibility of the slopes of the parallel and perpendicular lines. We should have done better in this unit than we did, but if you are still struggling, here is your chance to prove that you can do better.